Hello, welcome ladies and gentlemen. Now we're going to look at lesson 1.6, Introduction to Continuity, and we're going to look at again some of the examples to help you get through the examples, which will in turn help you better understand how to do the problems and application of the problems. Okay? So we're talking about continuity and one-sided limits. A step up from our previous lesson 1.5. Okay, let's get into it. First example. Let's see. So here's continuity and what it actually means. Informally, the graph is the graph that can be drawn without lifting the pencil from the paper. And here are the three conditions. Okay? Here are the three conditions that define a function being continuous. So a function is continuous at a value c if all three of these conditions are satisfied. 1, f of c is defined. 2, the limit as x approaches c of f of x exists. And 3, if condition 1 equals condition 2. See? If the limit as x approaches c of f of x equals f of c, which is condition 1. So that's what defines a function that is continuous. If these three conditions exist. All right, example 1. Here we go. Let's take a look at example number 1 here. All right, so first, let's see if this is continuous. Well, let's look at f of 1. F of 1 is condition number 1. F of 1 equals 3 times 1 minus 1, which is 3 minus 1, which is 2. All right, so the first condition gives me a 2, give us a value of 2. Here's the second condition. The limit as x approach 1 of 3x minus 1 must exist. Does it exist? Well, plug in 1 for x, direct substitution. Plug in 1 for x. What do we get? We get the limit as x approach 1 of 3 times 1 minus 1, which equals 3 minus 1, which is 2. Okay. And then condition number 3 states that the limit as x approaches c of f of x has to equal f of c. In other words, condition number 1 must equal condition number 2 to satisfy condition 3. Now, does condition 1 equal condition 2? And if your answer is yes, then that's the answer. Yes, they are equal. Then condition number 3 is answered. Okay? And so this function is continuous at x equals 1. That's the point. So this is continuous at x equals 1. There you go. All three exist, are true. Okay. Let's look at our next example, example 2. Testing for continuity. Let's see here. Here we go. All right. Condition number 1. Let's see what f of 3 is. Equal. Well, plug in 3. 3 squared minus 9 over 3 minus 3. 9 minus 9 over 3 minus 3 is 0 over 0. This is the indeterminate form. Oh my, that's not too good. That's not good at all. If we cannot determine a value of the function, that's a problem. That's indeterminate. Well, okay, let's go to condition number 2, and let's see what happens in condition 2. All right, condition number 2 says, well, let's see if the limit as x approach 3 of x squared minus 9 over x minus 3, let's see if this exists. Let's see if it exists. Well, if I take 3 and directly substitute, I'm going to get 0 over what? 0. Indeterminate. That is the indeterminate form. Okay? So we have to manipulate the function here to re-express the function and then evaluate the function. Okay? So let's re-express the function using the cancellation or the factoring technique that we talked about in our last lesson. So it has to be rewritten as the limit as x approach 3 of x minus 3 times x plus 3 divided by x minus 3. And then we can begin to cancel out here, the cancel. This binomial cancels, the binomial in the numerator cancels the binomial in the denominator. So let's cancel those out, or better yet, they divide to 1. Okay? So we divide, and they both go to 1, and we're left with x plus 3. So we have now the limit as x approaches 3 of x plus 3. And what does that equal? Once we do direct substitution, we get a value of 6. All right, so that's condition 2. All right. 3. And so condition number 3 states that condition 1 has to equal condition 2. Well, condition 1 does indeterminate form equal 6? Does the indeterminate form equal 6? And the answer is no. Therefore, condition 3 fails. So we can conclude that this function x squared minus 9 divided by x minus 3 is not continuous at x equal 3. Okay, so f of x equal x squared minus 9 over x minus 3 is not continuous at x equals 3. Not at all. Because condition 3 fails. Okay? And furthermore, really, condition 1 really fails too. Because f of 3, that's not defined. There's no definition for the indeterminate form. We really could have stopped with, condition 1. But we took it a step further just to show you that condition 1 does not equal condition 2. Okay? All right, let's go. Let's keep it moving. All right. Testing for continuity on an open interval. All right. Is the function continuous on these two intervals, 0, 2 for this function, and 0, 2 pi for f of x equals sine x? All right. Well, we know that f of x is going to be discontinuous at x equals 1. All right. So we are discontinuous at x equals 1. Okay. So this function x squared minus 1 over x minus 1 is not continuous on 0 to 2. It's discontinuous at x equals 1. Whereas sine x on the interval 0 to 2 pi, it is continuous. Okay? So this one is yes. We are continuous from 0 to 2 pi. That is continuous. So in essence, for the second graph, if we have a sine wave at 0, open circle, it goes up, comes down, right here at 2 pi. And this is 0. No holes, no gaps, we're good on our open interval. So on this open interval, we're good. No problem. Whereas with this function right here, we're going to have a hole at, that's going to be a line, and yet somewhere here at 1, let's see, x minus 1, x plus 1, all over x minus 1. The x minus 1s cancel out. They cancel out, which lets me know that there's going to be like a point of discontinuity at 1, right here. Right there at 1. In fact, it's going to be at 1. Let me raise the graph up just a little bit higher. Yeah. Right here at 1. And let's draw it like this. Open circle and keep it going. There we go. And we're between 0 and 2. And we'll call this 2 right here. And we'll stop right there. Between 0 and 2. All right. There we go. So between 0 and 2, that defines our graph. And at 1, we have an open circle. So it's undefined there at 1. Okay? All right. Let's go. All right, testing for continuity on a closed interval. And one-sided limits here. All right, so we have the limit approaching from the left, limit approaching from the right. So now we're looking at each side. What's happening with the, what's the function doing regarding the left approach and regarding the right approach? What's happening with the function regarding each side of the function? Okay, at a certain value. For example, let's consider the graph, the square root of 3 minus x. Let's graph that. Let's sketch that graph. Well, let me see, 1, 2, 3. All right. And now, this graph goes back over in this direction. All right. This is a sketch of the graph. Okay? That's the sketch. In fact, let me draw the scale a little bit better than that. Because we know that when x is 0, y is 3. So when x is 0, y is the square root of 3. So it's a little bit more than 1. Yeah, let's put it about right there somewhere. Scale it just a little differently. All right. There we go. That's a little closer to form. So that's the graph. Now we want to know what is the limit as x approaches 3 from the left. See, this minus sign right here means what? From the left. Well, that's the only way we can approach this graph at 3. Because there is no graph on the right side. So we can't come to 3 from the right. Nothing there. We can only approach 3 from the what? Left. Let's do that. So here you are walking. You see? And you're walking from the left side. and you're getting closer to 3. You're getting closer to 3. And as you walk and you get closer to 3, what is your y value at 3? Your y value is what? Say it again, I can't hear you. Right, it's 0. That's the limit. Because remember now, when we refer to limit, we're primarily talking about y values. Unless it answers like infinity or doesn't exist, but if there's a value for the limit, it's the y value. It's the y value. And the y value here is 0. So that's our answer. Okay? All right, let's go. Let's go. All right. Now we're looking at the greatest integer function, or the step function. Okay. Here's what I want you to understand about the step function. This part right. Wait a minute. Go back. Yeah. Now, another one-sided limit is investigating the behavior of the step function, which is also called the what? Greatest integer function. Okay, well, why is it called the greatest integer function? Well, it's called the greatest integer function because where is it written out here? Because all right, here we go. Yep. Because we want the values of x, which is the greatest integer, less than or equal to x. So it's the value of x that is less than or equal to x. So remember, less than, that means go to the left. So less means left. Okay? Left means left. Oh, wait. That's my left hand. I should be going that way. Yeah, you look at me. Left is that way. Pardon me. This is my left. This is your left, right? Okay, gotcha. That way. Okay. Let's graph it. Let's take a look at it. So let's graph f of x equals greatest integer function x plus 2. So here's how you want to start. You want to have a column for x, a column for x plus 2, a column for greatest integer function x plus 2. That's everything we need. Choose your value of x. Let's start off with -2. Alright, let's say x is -2. Then what's the value of x plus 2? 0. And what is the greatest integer less than or equal to 0? Easy, it's 0. What is the greatest integer less than or equal to 0? Well, 0 is an integer, so it's just 0. Okay? Alright, great. Now let's go down to, let's say, -1.5. Put in -1.5 into the function. So I'm going to have -1.5 plus 2, which is -1.5 plus 2 is 0.5. Okay. So I have 0.5. And what's the greatest integer? 0.5. What's the greatest integer less than? are equal to 0.5? 0. Okay. Now, let's do -1. Well, hold it. I want you to notice something here. -2 value for x gives me a 0. -1.5 gives me 0. Let's plug in -1. Let's see what happens. Put in -1, put in -1 here. I'm going to get 1. And what's the greatest integer? Less than or equal to 1? Well, it's 1. Here's what I want you to understand. All of the values, all my values here, not including 1, come on, purple. There we go. Not including -1. But all of the values here, all going all the way toward -1, is going to give me a y value of 0. So all of those x values, let's graph it. At -2, I had a 0. -2, 0. -2, 1, 2, it was 0. At -1.5, it was also what? 0. -1.5, 0. All values in this interval right here is going to lead you back to 0. What do you mean all values, Mr. Wright? I mean, if you were to look at -1.7, that's going to give you a 0. -1.6, that's going to give you a 0. -1.4, that's going to give you a 0. All values in here is going to give you a 0. So you got 0 all in this region right here, with the exception at -1. Here's the switch. At -1, we're at 1. So go over -1, up 1, close circle. And here we're going to have an open circle. So it's all of these values in here, except at -1. All right? And then we do it again. At -1, we get 1. All right, let's look at some more intervals. All right, how about -0.5? Plug in -0.5 right here. At -0.5, what do we get? We want to get 1.5. All right, now, what's the greatest integer? 1.5. All right, that's going to be the integer less than or equal to 1.5. The integer less than or equal to 1.5 is 1. Okay? And it goes on and on and on and on and on and on. So from -1 over to 0, we shade it, open circle at 0, because now we've looked at -2, we looked at -1, now let's look at 0. What's happening with 0? Put in 0 for x, what do you get? 2. Greatest integer, 2 is 2. Oh wow, so I have 0, 2. 0, 1, 2, okay? Now, let's make our way over to 1, because we had 0 right now. Let's look at 1.3. 1.3, plug it in. We're going to get 3.3. No, oh, we can't do, I'm sorry, not 1.3. I'm just 0.3. Pardon me, 0.3. There we go. Let's look at 0.3. All right? Take 0.3 and plug it in. What do we get? 2.3. What's the greatest integer 2.3? 2. All right, look at 0.4. We get 2.4. What's the greatest integer 2.4? 2. So everything between 0 and 1, well, not including 1, but everything between 0 and 1, 0 and 0.99999 is going to all map to 2. So from 0 all the way over to 1 is going to map to 2, open circle at 2. Okay? And so as you can see, there's a pattern here. There's a pattern here. Closed circle, open circle, closed circle, open circle, closed circle, open circle. Okay? So this step function, it is discontinuous everywhere. It's discontinuous everywhere, and it's discontinuous, no, well, not everywhere, at every integer. Let me put it like that. At every integer is discontinuous. At every integer. -1, discontinuous. 0, discontinuous. 1, discontinuous. 2, discontinuous. There's a jump discontinuity on every integer. So it's discontinuous. All right. Last example. Determine the continuity of this function right here. Question, is f of x continuous? Yes or no? Is f of x continuous? Well, first of all, I notice I have a piecewise function here. I have a left piece and a right piece. Consider 2, the number 2 here. All right? Now, this information is to the left of 2. This information is to the right of 2. Left side, right side. So look at both of the limits, the left limit and the right limit. So the limit as x approach 2 from the left side is this function here, 5x, 5 minus x. And then the other side, the limit as x approaches 2 from the right, well, then use the function down below, x squared minus 1. Look at both sides of 2 as evaluate the function f of x. So plug in 2 for x right here, what do we get? 3? Plug in 2 for x right here, what do we get? See, 2 squared is 4, 4 minus 1 is what? 3. Notice, the limit from the left of 2 is equal to the limit from the right of 2. They both equal 3. Therefore, the function is continuous. Therefore, f of x is continuous because f of x has 2, well, no, I want to phrase it like that. Put it like this. No, not like that. F of x is continuous because with 3 conditions. Of continuity are satisfied. And this, of course, being the third condition, okay? That the limit of 1, with the limit of the left side equals 3, and the limit of the right side equals 3, which means the limit of the left equals the limit of the right. and they're both defined at 3. So it's continuous. Okay. Very good. See you next time. Bye.